Hello. Last time we talked about the stereochemistry. It's an important part of in terms of the structure of organic compound. Now we are moving our focus from the structure to reactions. Reactions deals with the change over the time, and we'll divide this chapter into two parts. The first part will provide the basic concept on the organic reactions, and the second part describes the organic reactions in terms of the time and energy. Why do we learn this chapter? In order to understand organic chemistry and biochemistry, particularly for the biomolecules, it is necessary to understand what is happening inside of the cells or inside of the molecules, and why does it occur, and how the change is possible. We will see the basic concept of the organic reactions and systematic way to describe reactions. There are several kinds of there are so many organic reactions. We cannot learn all of those reactions, so we just classify all organic reactions into few groups, like addition, elimination, substitution, and rearrangement. This kind of classification is based on the type of change of the molecules. Two molecules are added together in addition. You remove one molecule from part of a molecule, and it's an elimination. Some part of atom or atomic groups are substituted by other kind of atom or atomic groups, then we call substitution. Rearrangement is just a rearrangement of the bond without changing atoms or atomic groups. So, and we'll describe details of all of these types of reactions later. Before we talk about this kind of these types of reactions, we have to introduce a few concepts. The concept of the mechanisms. Just like if you look at the clock, hands of the clock is moving, indicating minute and hours. But the detailed mechanism of moving those hands, those needles, are behind of the clock, and we cannot see it. Organic reactions mean the change of molecules from the reactant to the product. Change of a reactant to the product includes transformation of the molecules, reactant molecules, into the product molecules. And the transformation means change of chemical bonding in the reactants. And the mechanism means the description of how those change occurs inside of the molecules. Now, when we talk about the mechanism, we can divide the mechanism into two different kinds of things. One is lysis, that means you break molecules. And the other part of the mechanism will be mechanism of reaction will include genesis. Also, in this lysis and genesis involves breaking of the bond, and we know all chemical bond consists of two electrons. Two electrons are paired and forms a bond. Therefore, when they undergo lysis or genesis, we have two electrons here. Here we have two electrons. When the chemical bond is broken, we can imagine both of electrons moves to B, and B becomes -1 charge, and of course A will become +1, right? We call this as a heterolytic cleavage because the cleavage of electrons is not symmetrical. That means heterolytic, okay? That's what it means, hetero. But if you break this bond by dividing two electrons equally, then we call homolytic. That means each of these two electrons goes to each atom, A and B, right? That's the way to break the bond. So when you break the bond, could be heterolytic, like this, or it could be homolytic. However, we can apply the same concept for the genesis of the chemical bond. For example, if you make this chemical bond by combine of A plus and B minus, then we can say it is unique because it generates the bond and started from unsymmetrical electronic distribution in two atom or atomic groups. So it could be, we can say hetero. So this is heterogenic formation of the bond. On the other hand, if you start from one electron in each atom and then make one bond, then we can say it's a homogenic formation of the bond. So in terms of breaking of the bond, could be heterolytic or homolytic. In terms of formation of the bond, could be heterogenic or heterolytic. But the more common word for heterolytic or heterogenic process is called the polar mechanism. If the reaction involves homolytic cleavage or homogenic synthesis of the homogenic formation, then we call this a radical mechanism. So in terms of the distribution of electrons in the formation or breaking of the bond, whether it is a symmetric distribution or whether it is unsymmetrical distribution, we call, if it is symmetric distribution, then we call radical mechanism. If it is unsymmetric distribution, it follows unsymmetric distribution of electrons, then we can say polar mechanisms. Generally, most of organic reactions we see in a cell or in a living materials involves polar mechanism rather than a radical mechanism. However, the radical mechanism is simpler to understand than the polar mechanism, right? We introduced the two different way of organic reaction mechanism, polar and radical, but we'll introduce radical mechanism first because it's simple to understand. But remember that most of reactions actually involves polar mechanism, okay? Whether it is a homolytic, heterolytic, or homogenic or heterogenic, the reaction involves redistribution of electrons. And in order to redistribute the electrons in the chemical bond, we have to show or we have to indicate the moving of electrons. When you show the moving of electrons, the head represents the number of electrons. Okay, if you have a half head like this, it's the moving of one electron. If you have complete head like this, then it indicates two electrons. Therefore, complete head will indicate heterolytic or homogenic steps. That is the polar mechanism. And half head will indicate half head will indicate homolytic and homogenic steps and called the radical mechanism. Therefore, half head is used to describe radical mechanism, is used to describe or to describe the moving of electrons in radical mechanism, and complete head is used to indicate the moving of two electrons in a polar mechanism. I told you most of reaction involves polar mechanism, and in most of reactions, the mechanism will use complete head. As I told you, the radical reaction is simpler. So we start the radical mechanism first before the polar mechanism, right? Radical means it's not stable. Radical is radical, right? So most of radicals are in high energy because they are in high energy. They are not stable. They are unstable. Because they are unstable, most of radicals are ready to undergo chemical reactions. For example, if you have a radical like this, so radical means you have one unpaired electrons. Then we call that is the radical species, okay? Because the radical is generated by homolytic cleavage of chemical bond. So the result, the radical species will have one unpaired electron. Because they are in a high energy, they will readily react with other organic compounds. And the unpaired electron wants to make a pair with another electron, so they abstract one electron from the other molecule. For example, here, they will, this radical will abstract the one electron and then form one chemical bond between red and A, but it will generate another radical here. So this is the reactant, and this is the product of the radical process. Let's take an example. This is really example of the radical of the organic reactions involving radical mechanism. methane reacts chlorine and forms chloroform and HCl. This reaction requires the light. Actually, light provides energy to generate radicals. So H nu is a light energy, provides the energy to break this bond, and this is homolytic process, okay? Because I told you this undergoes a radical mechanism, so this should be a homolytic process. That means two electrons here will be symmetrically cleaved, so it will generate chlorine radical like this, and here is one unpaired electrons. Energy of this chlorine radical is relatively high. It's higher than chlorine molecules because these radical molecules absorbed the energy from the light. Because this chlorine radical is highly energetic, it will react with methane. Methane is a stable, relatively stable organic molecule. However, you have two electrons here and here. It will abstract one electron to make a pair and becomes HCl. And the result is the generation of another radical, that is a CH3 radicals. When chlorine atom abstract electrons, they abstract electrons on the part of the hydrogen rather than CH3, okay? Don't confuse, right? Now you generate another radical, and this radical will react with the chlorine, that's the reactant, and generate chlorine radical again. There's a typing error. This H should be removed, okay? And this chlorine radical goes back here, and the cycle continues. Therefore, we call this initiation step, because this initiation step involves initiation of the reaction. In order to initiate the reaction, you have to generate radical, and the generation of radical became possible because you provide light energy. So actually, the energy source for the generation of a highly energetic radical comes from light energy. Now, in next step, the chlorine reacts and generates methyl radical, and methyl radical reacts with chlorine reactant molecules, then regenerate chlorine radical again, and so it can go to here and continue. Because this regeneration of chlorine radical makes it possible to circle the reactions until they consume all the reactant molecules, the starting materials. After they consume all of them, you will have you are going to have two different kind of radicals. One radical is chlorine radical, and the other radical is methyl radical, okay? So try to think about the combination of these two radicals. We can imagine combination of two chlorine radicals, combination of two methyl radicals, and combination of methyl radical and chlorine radical. So that's the way how you are going to how the radical species disappeared in this system. After radical species disappeared, the reaction will stop. So this disappearance of the remaining radical species is called termination, right? So we can expect three different kinds of molecules from the termination step. okay, because there are three possible combination of two radical species. So the radical reaction generally involves three steps, as shown here: initiation, propagation, and termination. In this reaction, we should remember that what is the initiation of this reaction, okay? The chlorine molecules. Where does energy is provided to initiate this radical reaction? Energy is provided by, and then we should be able to what kind of propagation step will involve, right? Once you generate that chlorine radical species, you have two reactant molecules. Okay, so either react or not, the other reactant molecules, of course, the result like this. And because this methyl is energetically very high, they readily react. And where is the reactant? And the other reactant is here. So you get here. Obviously, we'll produce the one over product, and cell radical will continue the propagation steps. In this propagation step, because you continuously repeat this propagation step, you will continuously produce HCl and CH3Cl as the product of this reaction. Okay. Until this propagation step will continue until you consume all reactants. Okay. Once you because you consumed all the reactants, the things remained in your reaction vessel will be a radical, and we can imagine three different kinds of radicals: chlorine radicals and CH3 radicals. Because you have two different radical species, the combination of two radical species will result in three different species. Okay, so that will be L2, that will be ethane, and combination of Cl radical and CH3 radical will be CH3, and this is another production of the product CH3Cl. Okay, so it's a generalized mechanism of the radical reactions. Polar reactions. As I told you, polar reactions involves unsymmetrical movement of electrons. Because the movement of electrons is unsymmetrical, you have to decide where those electrons go to. And the electronegativity of an atom is the most important factor in the direction of moving of electrons. O, F, and Cl. Those are very electronegative atoms. Okay, so if some other atoms attach to this kind of electronegative atoms, then two electrons will move to this kind of atom. Okay? And the other part of the other counterpart of the atom will lose it. Let's take an example. This is an example how the bonds are polarized. For example, here, COH is polarized, like C is plus and O is minus. So if this bond undergoes catalytic cleavages, OH will be minus and C will be plus, right? We can take an example for many other kind of polarization. For example, here C and X is halogen, so there will be a polarization like this. in this polarization or in this polarity, the electronegativity of an atom plays the most important role to determine which atom is plus and which atom is minus. Okay? Sometimes if the carbon is attached to the metal species will be positively charged and carbon will be negatively charged. In most of cases, the carbon is positively charged because a lot of atoms that we are interested in biomolecules attached to the carbon is heteroatoms like sulfur, oxygen, nitrogen, halogen. All right, so obviously the carbon will be positively charged. Now we understand what the polarity is. The polarity is plus or minus charges, and if the polarity is very high, that means the polarity of the bond, if a bond has high polarity, that means the bond, one of two bonds, one of two atoms in the bond are positively charged and the other part is negatively charged. And the polarizability is a slightly different concept for the polarity. It's important to distinguish and understand important to distinguish the polarizability from the polarity and understand the difference in the concept. Polarization is a change in electron distribution as a response to change in electron nature of the surrounding. Okay, so the polarization is change of electron distribution due to change of surroundings. All right, so actually the polarization is an induced property. When the surrounding is changed, and then the electronic distribution in the chemical bond is changed. So this change is kind of induced by the surrounding, right? And the polarizability is the polarization ability, and that is a kind of a tendency to undergo the polarization. So if you have a high polarizability, that means it has a high tendency to undergo polarization. It is not polar under the certain surroundings, but when the surrounding was changed, and this change of surrounding can cause the polarization. If the polarizability is very good, if the chemical bond has high polarizability, then means if the surroundings changes, then the bond will be easily to undergo the heterolytic cleavages or heterolytic genesis. All right. For example, here, in this case, C and S, that we can describe carbon is delta plus and sulfur will be delta minus. In this case, iodine is delta minus, carbon is delta plus, and we can say this bond is polarizable bond, right? Because it can produce the polarity here. But when you compare two molecules, for example, here CH3, Cl, and CH3 and Li, in this case, carbon is delta plus and Cl is delta minus, of course, all right? However, if it is attached to the metal like lithium or magnesium or calcium, then this will be plus, this will be minus. So the property, electronic property of the carbon strongly depends on what is attached to the carbon. All right, it is attached to the carbon is attached to the electronegative atoms, then carbon will be positively charged. But the carbon is attached to the metal ions, then the carbon will have negative charges. Okay. So the polarity will depend on the electronegativity of two atoms. Okay, electronegativity difference between two atoms, right? That will determine which part is minus, which part is plus, right? So electronegativity of this each of these is an important factor, whether they are going to have a plus charge, minus charge, or plus charge, or minus charge. Now it's important to understand the difference between polarity and polarizability. Right? Let's take a look at here. This is carbon. This is fluorine. So if we look at this bond, carbon and fluorine, this bond, this will be delta minus, and this will be delta plus. And we know that this fluorine, electronegativity of this fluorine is very high. Therefore, this bond will be very polar bond because there is big difference in the electronegativity between fluorine and carbon. So the charge, the size of the charge will be very large, and then this bond will be very highly polar bond, very polar bond. Okay. Now let's take a look at, let's compare this bond with this bond. All right. In this case, this is iodine. Right? Then the size of the iodine is much larger than the fluorine. All right. So fluorine, the bond length between carbon and fluorine will be shorter compared to the bond length between iodine and carbon. Even though the electronegativity of the iodine is not higher, is lower than the electronegativity of the fluorine, but this bond is still polar. If some surrounding happens, if if there is a driving force for breaking this bond is easier to be broken because this bond is very long compared to short step bond. CI bond is longer than the CF bond here. Because the bond is longer, it will be easy to be broken. When the bond is broken, the electronegativity of iodine is higher than the carbon, so the iodine will be, the bond will be cleaved and produce iodine minus and carbon plus. And in this case also, the bond will be broken and then it will produce F minus and carbon plus. However, the bond length is very short because for the size of the protein is so small, and but iodine is very large, bond length is very high, very long, it's very long bond length, easy to break. Therefore, the result will produce I minus and C plus, and then due to long bond length, it's easy to break, easy to produce I minus and C plus. So actually, this one is not polar. It's not very polar because the electronegativity difference between carbon and iodine is very small. However, the bond is very long and easy to break. And once it is broken, then the I will be charged as minus, carbon will be charged as a plus, just like polar bond. So in this case, we say the CI bond is polarizable bond. Okay, it's not polar because the electronegativity difference is not large. However, it's easy to break because the bond length is large due to the huge size of iodine compared to the fluorine. Okay, actually, in many reactions, in many organic reactions, polarizability is more important than the polarity. Okay, so try to remember the difference between polarity and polarizability, and also remember that in many cases, polarizability is more important than the polarity. Okay, now I explained half-headed arrow and complete arrow in previous slides. In polar reactions, we usually use complete arrow, all right, to indicate the moving of two electrons. Like here, B minus and A plus. Then you have two electrons on the B minus, then A is plus because it's short of electrons. Because it's lacking electrons, it will accept electrons, and this will be have more electrons. One electron. You have one more electron, one more extra electrons, and we call this is nucleophile. We call this is electrophile because this is positively charged, likes electron because electron has negative charge. Because this is negatively charged, it likes nucleus because nucleus has a plus charge. Okay, so nucleophile generally is electron rich. Electrophile is generally electron poor. That means lacking electrons, right? If they make a bond like this, it's a two electron, and two electron comes from both of electrons from B, right? So the two electrons in the B moves to A and make a bond, right? So when we show the movement of electrons, we should show the movement like this, okay? Make a bond. Now, generally, now we have now I introduced the concept of nucleophile and electrophile. It is very straightforward that most of nucleophile will have a negative charge. Or if it is neutral, then the nucleophile should contain non-bonding electrons. Okay, that's the requirement. Otherwise, they cannot behave as a nucleophile. Okay, most of nucleophile can behave as a nucleophile because either they have a minus charge like this, or either they have non-bonding electrons. Because of the non-bonding electrons or negative charges, they have a tendency to provide electrons and to make a bond. Generally, electrophile is short of electrons because they are lacking electrons. They want to accept electrons, right? And to make a bond. Of course, those electrophiles will have opposite properties of the nucleophiles. So the electrophiles will have plus charge, or electrophile will have electrophilic atom will have a delta plus due to polarity or polarizability. For example, here H3O plus is electrophile. Okay. Also, the electrophilic atom in H3O plus is H plus. All right. In this case, CH3 delta plus, and actual delta plus is on the carbon here. So this carbon is electrophilic center. Actually, this Br, we can say this Br is a nucleophilic center. Actually, this Br has number of electrons like this. And in this case, this will be electrophilic center, and this will be nucleophilic center. I didn't draw it, but you should have number of electrons like this. Let's take an example. Let's apply the concept of electrophile and nucleophile for some kind of chemical reactions. The concept of nucleophile or electrophile is very important, okay, for to understand organic reactions. But it's easy to understand. The condition for the nucleophile is whether they have a minus charge or whether they have electrons. Okay. On the other hand, the electrophile should have a positive charge or they are short of electrons. Therefore, most of the nucleophiles will behave as electron donor. Okay, and electrophile will be electron acceptor. Hmm. Let's take an example here. Let's and apply the concept of nucleophile and electrophile here, right? In this case, we have a CH3 and reaction of CH3 and AlCl3 and forms AlCl4 and CH3 plus. Okay. Um, I need a whiteboard. I'm going to use the whiteboard to explain, to apply the concept of nucleophile and electrophile for these reactions. Okay, let's go to right. Let's go to the whiteboard. Um, the reaction we are going to talk about is CHCS3 and ALCS3, right? We have a Cl and Cl plus Al. Let's try to identify the electrophilic center and nucleophilic center in this reaction. Um, if you look at the product, so the product is CH3 plus and yeah, ASL4 minus. Okay, so we draw the Lewis structure. It will be like this. Let's yeah. Now here we know the electronegativity. Let's focus on this bond. Okay, and try to use the red color here. We have two electrons here, right, to make one bond. And actually we have four pairs of numbering electrons on the chlorine. And we know this bond is a polar bond. And if you have to break this bond, it will be heterolytic break. So these two electrons will be broken. This bond will be broken, and these two electrons should move. Because this includes the polar mechanism because of the electronegativity difference between the Cl carbon, the electron should move. Now you have to decide whether these electrons to move to carbon or whether these electrons to move to chlorine. Obviously, two electrons will move to chlorine, okay? So you have to draw arrow like this. And then it becomes CH3 and you will generate Cl minus. Okay. Now here, if you look at here, all this chlorine will have oops, whoa, wow, 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 wow. 공유 링크, 웹 공유 링크 끝. I'm gonna. Oh wow. All right. All this. Oh wow. That's why I understand why. All this chlorine have numbers like this. Oh yeah. Uh, and we know we have only here, but the aluminum has only three electrons here. And if you count all electrons around the aluminum, will be only six. Therefore, aluminum is short of electrons. It will be an electron acceptor. Therefore, aluminum is electrophile. In this case, this is nucleophile. This is electrophiles. Therefore, the reaction should occur from this one as a nucleophile, and this one, this is electrophile, so this should react with nucleophile, right? Now you don't have any choice. This is the only nucleophile you generate here. Therefore, the reaction will occur between nucleophile and electrophile, and the way uh, this are the bonds you originally had, but this is a new bond, okay? And this new bond comes from the electrons for this new bond comes from these two electrons on the chlorine, okay? Therefore, we should indicate the movement of these two electrons by a complete arrow, like this, and make this. Um, but in this case, the aluminum has three electrons around the aluminum, and it's neutral, right? Try to understand the formal charge. Here you have one more electron surrounding aluminum, so the aluminum should have minus charge, right? And you still have the CH plus as a nucleophile here. So this is how you generated uh, how you generated ASL4 minus and CH3 plus. Okay. Now let's think about the next step. The next step is the reaction with the water, right? Now, if the water reacts with the CH3 plus, then this CH3 plus is a electrophile, and water could be electrophile or could be nucleophile. But in this case, if the water wants to undergo the reaction this is with CH3 plus, then the water should behave as a nucleophile, and oxygen has two pairs of non-bonding electrons, and it is qualified to behave as a nucleophile. So you should indicate the movement electrons, okay? Two electrons move to the carbon and then form CH3O, and so actually this bond is a new bond uh, by the movement of these electrons, okay? And try to take care of the formal charge, right? In this case, the oxygen is neutral because oxygen has 1, 2, 3, 4, 5, 6 electrons. But once these two electrons are used to make a bond with the carbon, then oxygen will have only one electron on oxygen side. Therefore, oxygen should carry a +1 charge, right? Now, in this case, oxygen is positively charged. Because oxygen is positively charged, it's not stable. Oxygen's electronegativity is very high. Oxygen doesn't like to have a positive charge. Therefore, the oxygen will attract electrons between O and H and take all two electrons on the oxygen and kick out H as H plus. Okay, so that's how we generate H3OH and H plus. Let's take a look at another part. In this case, let's apply the nucleophile electrophile concept uh, for the reaction with CH3Br and magnesium, right? It's the same thing. In this case, magnesium is a nucleophile, and you should look for the electrophilic center in the CH3 uh, and in CH3Br, okay? So you can let's go back to the whiteboard. Hmm. Let me make a new whiteboard. Yes. Now we are going to think about the reaction between each and okay. Now in this case we have just a minute. I'm going to erase it and oh, through H3 and, and we know uh, this will be delta plus, okay, this carbon, and this bromine will be minus. But if you look at the research structure of the magnesium, magnesium has two electrons on the outermost shell. Now let's think about what would be electrophilic species and what would be the nucleophilic species. Here you have both. This will be nucleophilic center. This will be electrophilic center. Here you only have nucleophilic characters. Therefore, if you want to imagine the reaction between these two species, the because this is nucleophile, you should look for the electrophilic center on this molecule, and this carbon. That's the electrophilic center. So actually, these two electrons should move. Actually, should move to these carbons, and in the form like uh, like a um, like those magnesium will behave as an electron donor, it's a nucleophile, and carbon in CH3 will behave as a nuclear electrophilic center. So these two electrons move to carbon like this, and it'll be like Pr will be a Pr minus, Pr is Pr minus, and CH3 is just like CH3 plus. Just I explained in the previous slide. Now we can think of this magnesium will react with the CH3 and it will form a MgBr. That will be a minus, and CH3 that will be the plus, and oh, CH3 will be like this, like a minus, okay? Because CH3 is plus, but you will get two electrons from the magnesium. Both of these two electrons move to the carbon, then it becomes CH3 minus. You can easily understand what happens. This is plus, but magnesium has two electrons here, and these two electrons moved here. So uh, because you have two electrons moved. Oh no. And you will have two electrons like here. These two electrons comes from the magnesium, right? And that now you have one, two, three, four, one, two, three, five electrons on the carbon. So the carbon should have minus charge like this. Because the magnesium lost the two electrons, magnesium will have two plus, right? But the Br minus has minus one charge, so it will combine with Br minus, and actually MgBr will be like a one. Okay, this is minus one, MgBr is plus one. That's why you have That's why you have a CH3 minus MgBr plus like this. Okay. Now let's think about the reaction of this species with water here. And in this case, uh, CH3 minus is a nucleophile, so if it reacts with water, it should abstract protons. It will never react with the oxygen atoms because we know that the oxygen is nucleophilic center. This is electrophilic center, so because this is nucleophile, it will react with protons, right? And then when you show the movement of electrons, it should be like a complete arrow, right? Because you have two electrons in the carbon, right? And CH4 plus, okay? Hmm. Let's take a real example of a polar reaction. The easiest example of the polar reaction is an addition of one Pr to ethylene. Um, let's try to look at the structure of ethylene and HBr. And once you look at the molecules, you should try to identify the nucleophile and electrophile. Now, once you identify nucleophile and electrophile, you also have to identify where is the nucleophilic center in nucleophile and where is the electrophilic center in electrophile. If you have ethylene like this and HBr, we know the HBr is a Lewis acid, just like HCl. Because this is a Lewis acid, it should be electrophilic species. That means HBr is electrophile. On the other hand, the ethylene has two double bonds, and the double bond has two pi electrons here. And these two pi electrons, because of these two pi electrons, it can behave as a nucleophile. Because the HBr is an electrophile, the reason HBr is an electrophile is because you can easily break. That's the heterolytic break, heterolytic process, okay? And generate H as H plus. It leaves Br as a Br minus. Now HBr is a Lewis acid because H plus in HBr is electrophilic species. Because ethylene is nucleophile, it will abstract electrophilic species coming from HBr, that is H plus. So the first step of the reaction will be two electrons in the double bond will attack electrophilic center, electrophilic species H plus, and forms the first intermediate. And then once you form our first intermediate, then the next step will include Er minus, right? And form to produce this as a final product. Let's try to complete. I just explained the formation of a reaction between nucleophile and electrophilic species of H plus. Okay, that's the first part of the reaction. The second part of the reaction will include the reaction of Br minus. Okay, so let's take a look at this reaction in more detail. First step, as I told you, is a nucleophilic species. It's a double bond, moves complete arrow, right? Attack H plus, right? Leaves Br minus, and it will generate species like this. In this case, this H have a choice whether they will attach to this carbon or the other carbon. If H is attached to this carbon, you will generate plus on the other carbon, right? So actually, this is like a CH2, and you have a H attached to here, then you generate plus on the other carbon like this, all right? And now you have a single bond instead of a double bond. Because you have a plus charge on this carbon, this is electrophilic species, electrophilic center. Now, once a proton is attached to this part, then you will have Br as a Br minus. Br will be dissociated as a Br minus, and that Br minus nucleophilic species. So you can draw the arrow like this. It becomes this is a final product. One thing we can think of uh, is the is this carbocation species, and you have like you have carbon as a sp2 hybrid, and one p orbital is empty. Okay, we know the shape of the p orbital like this, and this p orbital is empty. Okay, and because p orbital is empty, not occupied by electrons, and that's why it likes Br minus, which is the electron-rich species. Okay, so this empty p orbital accept Br minus, and electrons in Br minus occupy this p orbital, changes into sigma orbitals, right? And makes a final product. I used the arrow to indicate the movement of electrons, all right? The complete arrow indicates movement of two electrons. Also, this arrow clearly describes direction of uh, moving direction of electrons. Okay, be careful about the direction of this arrow. Okay, if you draw an arrow like this is the starting point of electrons, and this is where the electron arrives. Right, this is departure. This is arrival. Okay. Okay, I think this is the end of the first part of chapter 6. And next time we'll talk about the second part of the chapter 6. I told you that chapter 6 is divided into two parts, okay? So see you next time. Bye.